In episode 95, titled Naive Bayes, When Simple Probabilistic Models Shine, we focus on a family of classifiers that often looks almost too simple, yet routinely delivers strong results in the right settings. Naive Bayes is popular because it is fast, it scales well, and it provides a probabilistic intuition that can be easier to explain than many black box alternatives. In practical workflows, it also acts as a reliable baseline, meaning it gives you a solid point of comparison before you invest time and compute into heavier models. The exam-level challenge is to understand what makes it naive, why that naivety does not always ruin performance, and when it is a good choice versus when it is clearly the wrong tool. When you can connect its assumptions to data shape, feature type, and operational constraints, naive Bayes becomes less of a trivia topic and more of a useful decision option. This episode builds that decision intuition in a way that stays grounded in how the model behaves. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Naive Bayes is a probabilistic classification approach that applies Bayes' rule to estimate the probability of a class given observed features using a simplifying independence assumption. Bayes' rule describes how to update beliefs about a hypothesis when you observe evidence, and in classification, the hypothesis is the class label while the evidence is the set of feature values. The model combines a prior belief about how common each class is with a likelihood that describes how probable the observed features are under each class. The key simplification is that it treats features as conditionally independent given the class, meaning it assumes that once you know the class, the features do not provide extra information about each other. This assumption reduces a complicated joint probability into a product of simpler probabilities, which makes training and prediction extremely efficient. The model then compares class probabilities and selects the class with the highest posterior support under this framework. The independence assumption is called naive because in most real datasets, features are not truly independent, even after conditioning on the class. Words in text are correlated. Telemetry features co-move, and behavioral signals often travel in clusters rather than appearing in isolation. Despite that, naive Bayes often works acceptably because classification decisions depend primarily on relative comparisons between classes, and many dependencies cancel out or matter less than you might expect. The model can still rank classes correctly even when the probability estimates are not perfect because it is capturing the broad direction of evidence. In addition, when you have many weak signals, the independence assumption can act like a regularizing force, preventing the model from overfitting complex interactions that are not reliably supported by the data. This is why naive Bayes can produce strong practical performance even though its core assumption is technically unrealistic. The important exam-level lesson is that naive describes the assumption, not necessarily the outcomes. Naive Bayes shines in text classification and other tasks with high-dimensional sparse features because its structure matches the way evidence accumulates in those settings. Text features are often represented as counts or indicators for words or tokens, and each document contains only a small fraction of the possible vocabulary, which makes the feature matrix sparse. In sparse spaces, many models struggle because the dimensionality is high and the data for each feature is limited. But naive Bayes handles this gracefully by estimating simple class-conditional probabilities for each feature. It naturally supports the intuition that many small pieces of evidence can add up to a strong class signal, which is exactly what happens in spam detection, topic classification, or intent labeling. Because the model is efficient, it can be trained quickly on large vocabularies and updated frequently as new terms appear. This combination of speed and suitability is why naive Bayes remains a go-to tool in text-heavy classification problems. The speed and efficiency of naive Bayes are not accidents. They follow directly from the fact that the model does not need to learn complex interactions. Training typically reduces to counting feature occurrences by class and computing probabilities, which scales well even when the number of features is large. Prediction is similarly efficient because it involves summing log probabilities across the features present in an observation, rather than running iterative optimization. This makes naive Bayes attractive when you need to build quick prototypes, establish baselines, or deploy models in resource-constrained environments. It also makes it useful when you need rapid retraining due to drift, because you can refresh the model frequently without heavy compute. In operational pipelines, speed matters not only for convenience, but for responsiveness, and naive Bayes can offer that responsiveness. The trade is that simplicity limits the types of relationships it can represent. But when the data fits the assumption reasonably, the performance can still be strong. Interpreting naive Bayes outputs requires a careful mindset because the probabilities are best viewed as relative class support rather than guaranteed truth. The model outputs posterior probabilities under its assumptions, which means the numbers are conditional on the independent simplification and on the estimated likelihoods derived from the training data. In practice, naive Bayes probabilities can be poorly calibrated, especially in high-dimensional settings where evidence accumulates strongly and pushes probabilities toward extremes. That does not necessarily harm classification accuracy, but it does matter if you intend to use probabilities as direct risk estimates or to drive threshold-based policies. A safer interpretation is that higher probability indicates stronger model support for that class relative to alternatives, not that the numeric value is a perfectly trustworthy probability of correctness. This framing is especially important when stakeholders might interpret an output like 0.99 as near certainty. The exam often rewards recognizing that probabilistic outputs can be useful even when they are not perfectly calibrated.
There are situations where naive Bayes is a poor choice, especially when features are highly dependent and the signal is strongly interaction-driven. If the meaningful pattern is not just that individual features are associated with a class, but that specific combinations of features create the signal, independence assumptions can break down in a way that changes decisions rather than just affecting calibration.
In structured telemetry, for example, two features might only indicate an incident when they occur together in a specific sequence, and treating them as independent can produce misleading likelihoods. Strong dependence can also cause evidence to be effectively double-counted, leading the model to become overconfident or to overweight redundant signals.
When these interactions are central to the phenomenon, more expressive models or feature engineering that captures the interactions explicitly may be necessary.
The discipline is to choose naive Bayes when evidence accumulates roughly additively across features, not when the meaning is locked inside complex dependencies. A practical concept you must understand is the handling of zero probabilities, because in naive Bayes, a single feature with zero likelihood under a class can collapse the entire product and eliminate that class regardless of other evidence. This can happen when a feature never appears in the training examples for a class, which is common in sparse, high-dimensional spaces. Smoothing addresses this by ensuring that no estimated probability becomes exactly zero, typically by adding a small amount of pseudo-count to feature counts before converting them into probabilities. Conceptually, smoothing reflects a belief that unseen events are still possible, and that limited data should not produce absolute certainty about impossibility. Consistency matters because smoothing choices affect how strongly rare features influence decisions and can impact calibration and classification boundaries. The exam level point is not a specific smoothing formula, but the idea that you need a systematic way to avoid zeroing out probabilities due to finite sample effects. Comparing naive Bayes to logistic regression helps clarify when a simple linear boundary model is sufficient and when probabilistic independence offers a practical advantage. Logistic regression also often produces a linear decision boundary in feature space and can work well in many text and sparse feature problems, especially with regularization. The difference is that logistic regression learns weights through optimization and can better accommodate correlated features without relying on a strict independence assumption, while naive Bayes relies on class conditional likelihood estimates that can be more robust under extreme sparsity. In many settings, both can perform similarly, and the choice may come down to training speed, interpretability preferences, and calibration needs. Logistic regression probabilities are often more amenable to calibration and threshold policy design, while naive Bayes can offer a strong baseline with minimal tuning. The exam expects you to recognize that these are both reasonable linear-style classifiers in many contexts, and that the decision should be based on data characteristics and operational constraints rather than on mythology. When class prevalence is imbalanced, evaluation should emphasize precision, recall, and precision recall curves rather than accuracy, because naive Bayes can look strong on accuracy while failing to capture the rare class that matters. This is not unique to naive Bayes, but it is particularly relevant because the model's posterior probabilities incorporate priors that reflect prevalence, and that can shape predictions strongly. Precision and recall expose whether the model is producing useful positive predictions and how many true positives it captures, which matters when positives are rare and costly. Precision recall curves help you see the threshold trade-off and whether you can achieve acceptable recall without collapsing precision, especially if you intend to use the posterior probabilities as a scoring signal. If you use naive Bayes as a baseline in an imbalanced setting, you still need to evaluate it with metrics that reflect the decision problem. This keeps you from mistaking a prevalence-driven score for real detection capability. Communicating the strengths of naive Bayes is straightforward when you emphasize speed, simplicity, and baseline reliability rather than claiming it is universally superior. Its main advantage is that it can be trained quickly, scaled to many features, and often performs competitively as an initial model, especially in text classification and sparse feature spaces. It provides a probabilistic framework that is easy to explain at a high level, which can help stakeholders understand why certain features influence decisions. Its simplicity also makes it easier to maintain and to retrain frequently, which can be valuable under drift. At the same time, you should communicate that the independence assumption is a simplification and that probability calibration may need checking if probabilities will be interpreted directly. This honest framing builds trust and sets realistic expectations, which is exactly what professional governance requires. Using naive Bayes as a baseline before heavier models is a strong habit because it gives you a reference point for whether added complexity is truly worth it. If a complex model offers only a marginal improvement over naive Bayes, that improvement may not justify increased compute, engineering effort, operational fragility, or reduced interpretability. Baselines also help you diagnose data issues, because if naive Bayes performs unexpectedly poorly, it can indicate problems with feature representation, labeling quality, or distribution shift. Conversely, if naive Bayes performs surprisingly well, it suggests the signal is strong and can be captured by relatively simple evidence accumulation, which may reduce the need for complex modeling. This baseline discipline aligns with responsible model selection because it encourages evidence-based complexity rather than complexity by default. In exam contexts, stating that you would start with a strong baseline is often a sign of mature reasoning. The anchor memory for episode 95 is that simple Bayes plus independence yields a surprisingly strong baseline. The phrase surprisingly is important because it captures the practical reality that even naive assumptions can produce useful models when the data structure supports them. Independence makes the model computationally feasible and stable in high-dimensional settings, while Bayes' rule provides a principled way to combine evidence with class prevalence. The result is a classifier that often performs well enough to be useful and to serve as a benchmark for more advanced methods. Keeping this anchor in mind helps you avoid dismissing naive Bayes as outdated or overly simplistic. It also helps you avoid over-trusting it in settings where interactions and dependencies are central. To conclude episode 95, titled Naive Bayes When Simple Probabilistic Models Shine, name one use case and one limitation so you can justify it clearly. A strong use case is text classification, such as spam detection or topic labeling, where features are high-dimensional, sparse, and additive in their evidence contribution, making naive Bayes fast and effective. A key limitation is that when features are highly dependent and meaningful signal comes from interactions, the independence assumption can misrepresent evidence and lead to overconfident or incorrect decisions. If you add that smoothing is needed to avoid zero probability collapse in sparse spaces, you show you understand the main operational detail that keeps the model stable. When you can state a use case and a limitation this way, you demonstrate exam-level mastery without overcomplicating the model. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.